Hello everyone, today we're going to derive a really useful vector identity, which is the vector triple product A crossed with B cross C, and we want to show that's equal to A dot C times B minus A dot B times C. Now, one way to do this would be just to write out all of these cross products component-wise and do it that way. We're going to use a slightly more concise and powerful way, which involves using the epsilon symbol or the Levi-Civita symbol. Again, I'm going to assume that you have some familiarity with that. If you would like to see a more basic video on how this epsilon thing works, then let me know and I can do that. And so what I'm going to do is, firstly, just note that in general, we can write a cross product as follows, right? So if we take two vectors, let's say x and y, we cross them together, and we look at the ith component of that resulting vector, what we get can be written as epsilon ijk times xj and then yk, where summation is assumed over repeated indices. And this epsilon is the Levi-Civita symbol. Okay, so this is a really nice, concise way of writing out all the components of a cross product. And so we're just going to use that in the left-hand side of our equation and see how we can simplify it. So this implies that A crossed with B cross C, do that and take the ith component of it. That is going to be, just applying this identity with the epsilon, it's going to be epsilon ijk. Then our x vector here is basically A, so we get aj. And then the next thing we need is the kth component of B cross C, right? Because we've got a yk here, and this whole B cross C, that's like our y vector. Okay, so we have to take the kth component of B cross C. We're going to have to introduce some new indices, and we can write that as epsilon klm times blcm, right? So we've got two epsilons because there are two cross products, right? And so let's just put the epsilons together. So we get epsilon ijk, epsilon klm. Then what do we have? aj, bl, and cm. Now, if you watched my last video, this first bit might look familiar. This there's kind of a standard identity for this contracted product of two epsilons. We can write that in terms of the Kronecker delta as follows. So that is the same actually as delta IL delta Jm, where delta is the Kronecker delta. Then we subtract off delta Im delta JL, right? So we've just rewritten this product of two epsilons as this standard identity. I have a video on that if you want to go and see how to prove that. And then we still have this AJ BLCM stuff at the end. Okay, so what we can do is think about the restrictions that these deltas place on the indices. Now, what I mean by that is, so if we expand this into two terms, right, we have delta IL, delta JM, AJ, BLCM. And so, well, let's just keep the AJ as it is. But then this BL term, because we also have a delta IL multiplying that, and we're summing over the L's, we only get a non-zero contribution when I equals L, right? So the effect of multiplying by delta IL is to force L to be equal to I. So we can just change this BL into a BI, basically, and get rid of this delta. Now, similarly, we have delta JM times CM. We sum over the m's. The only time you get a non-zero contribution is when j is equal to m. So this kind of, the delta forces j to be equal to m, and so we just replace this m here with a j. So that becomes cj. And then we're going to do a very similar thing for the second term, right? So we subtract off delta im, delta jl, aj, blcm. Okay, and then let's keep this aj term as it is. This time, the second delta, delta JL, this forces J and L to be equal, so we can replace our BL with BJ. So there's that, and then we've got our delta IM, CM. delta IM forces M to be equal to I, and so we just get Ci. Now, notice that in general, if we have some vector x, right, and we have xj, xj, what does that mean? In fact, what we want to do is not consider that, but consider xj, yj, right? This means x1, y1 plus x2, y2 plus x3, y3, which is exactly the definition of the dot product, right? So this is just x dot y written in vector form. And you can start to see this is looking like what we're trying to prove, right? Because we've got aj, cj in this first term. That is just a dot c, right? So we can write that as a dot c times bi. And then similarly, the second term we have aj, bj, which is just a dot b, and then the ith component of c. But then we have all these subscript i's around. What we've shown, the fact that we have a subscript I on each of the terms, remember the left-hand side is this thing up here. We have an I subscript on each term, meaning it's true component-wise. It's true for any value of I. Therefore, it's true as a vector identity as well, right? And so this implies, because it's true for all three possible values of I, we can write down that A cross B cross C is equal to A dot C B minus A dot B C. So there we are. That's how you can concisely prove using the Levi-Civita symbol and the Kronecker delta, this vector identity. And one use for this, for example, is understanding the centrifugal force, because the centrifugal force has a mathematical form where you have a vector crossed with another two vectors. Okay, so I'll see you again soon.